So this is problem 2311, longest binary subsequence less than or equal to k. Let's start with the problem. We have two input. One is a string s and a positive integer k. And we are asked to return the length of the longest subsequence of s that makes up a binary that is less than or equal to the k. So subsequence, what is subsequence? Subsequence can contain leading zeros. So S is basically this 1010 string of 1 and 0. And the empty string is considered to be equal to 0. Okay, empty string is equal to 0. Subsequence is a string that can be derived from another string by deleting some or no characters. So it means that subsequence means what a subsequence from this s is any string that can be resulted if we delete some of this, but we don't change the order without changing the order of the remaining characters. So you can remove, but you cannot rearrange the order. So for example, in example 1, given the string s here and k is 5, the longest is 5, which is one of the valid one is 00010, which you can get by, for example, if you notice, there is no triple zero there, right? It's because what it does is it removes this and it removes this one, and then it got the 00010, which is, if we convert it into the 10-digit numeral, it means 2 to the power of this one to the power of 0, this one to the power of 1. So this is 2, and 2 is less than 5, right? So it satisfies the conditions. And so the second example, as is this, k is this, and then one of the solution is length 6, which we can get if you remove this and this. Okay, and you will get this value, which is, this means to the power of 0 times 1 is 1. 1 is less than equal to 1. Okay, so that's about the problem. Let's think about the tactic to solve this. Okay, so if you notice, we have this and we know what is a subsequence, we know what is k, and the tactic would be, let's take an example here. Okay, so we know that we can create a subsequence of s by removal, right? But the question says, how do we explore, how do we find a way to find the longest one we can get? The longest one we can get, it means the longest subsequence length we can get means as minimum as possible the number of removal that we do. That is equivalent to get the longest possible. The minimal removal is the longest possible, okay? Keep that in mind. So how do we know how to go explore to find the minimum removal we need to do? Because this is binary, we know that the left one, the digit on the left side, the more to the left is the biggest contribution numbers, right? And the one that is contributing to the number is always the digit that turns into 1. The one with 0 doesn't contribute anything into the value. So we can get into the minimum possible that we need to remove in order to satisfies the requirement for the value to be less than equal to k is by starting to remove it from the leftmost. That's why if we start here, for example, we know first we can calculate what is the value here. The value here is 1 to the power of 1 is 2, plus 1, 2, 3. 2 to the power of 3 is 8 plus 3, 4, 5, 6. To the power of 6 is what? To the power of 6 means to the power of 3 times to the power of 3, 64. Okay. So this will be about 74. And 74 definitely is greater than 5. Then we start removing it from the leftmost. If we remove the leftmost, the subsequence become this, right? And this will result to 2 plus 8, which is 10. And it's still bigger. So what else can we remove? We remove the leftmost one, the leftmost digit 1, which is this one. We remove this one. So now the new digit will be this, and this will be 2, and 2 is less than equal to k, and there you go, we got the solution, the length of this string, which is 5. So the length of the strings sub s, which is 5, this is the solution, and we know that that was the solution, right? And we cannot get it more minimum than this because we already tried to remove from the biggest contributor. So there is no possible way we can get anything better than this. So that's it. That's the strategy. Okay. Basically, we got the tactic based on the after we realized the idea that the longest subsequence is equivalent to the minimal removal. And we can explore the minimal removal by trying to remove from the largest contributor. And the largest contributor in a binary is the digit 1, the leftmost digit 1. Okay, so from there on, let's start. First of all, we know some situations of we need phi, right, which hold the value here, and then we need first to actually calculate what is the value, which we can by looping in through the s. So if we loop one by one, we know that phi will be plus equal to the power of, let's say if this is 2, length 2 only, it means that this will be 0, I0, and we have n2, but we want to the power of 1. So it means n minus 1 minus I. Okay, so from the leftmost we need to take on the length, and then the length minus 1, and then minus the current iteration we have, because this will explore the string digit of the string from left to the right, but the power, the 2 power is actually biggest on the left, right? And then after we have that, we need to also because we want later on to find the minimal by trying one by one, removing the leftmost. So we need to make it efficient. Let's store this value into an array, and then we will remove it in order later on. And we are already in order from the biggest by doing this kind of looping. So we need to append this. So to avoid repetitions of calculation, we can just store it in a variable and pass it here and here. Okay. So once we get the phi of the whole s, we can check right away. If phi is less than equal to k, then we know the whole length of s is the answer, because we haven't done any removal, you see. Otherwise, we need to try to remove it one by one. For I in range 0 to length 1. Okay. So what we need to do here is v once I. Remember, we store the value contribution of that digit 1 for each of these membership. So we start to remove it from the leftmost, the biggest contributor. Then for each of it, we do this check, the same check. If v now become less than equal to k, which is fulfilling the requirement, then we just need to return n minus I minus 1, because I starting from 0, but the 0 index is actually contributing to 1 removal already. Okay, so that's about it. If we should find something somewhere there, or otherwise we find nothing, it means 0, empty subsequence. If we cannot find anything at all after removing all the ones we have, which kind of impossible, we will get 0 too, but just for the sake of completion I put this in. So that's basically how we translated the tactic into the code implementation in Python. Let's try this with the example test case. Wait, the answer is wrong. Where could we go wrong here? Return n minus I minus 1. My answer is 2 and 1. N is the total length. V minus 0 delta V. Let's try to return the delta, the ones first. 64, 32. Wait, what happened here? Oh, I know what's wrong. Because we should check it first if Si is equal to digit 1. Otherwise, we don't do this. This is only happening if Si is equal to 1. Okay, now I believe we should get the right answer. Submitting too soon. There you go. Let's now submit for the solution. Accepted pretty fast. Cool. Now the time complexity of this. The time complexity of this is just assignment, big O1, big O1, big O1. This is a looping. This is big O(n), where n is the length of the string s. This is just comparison. Big O1, big O1, big O1. This is just big O1. This one big O ones, where the worst case is everything is digit 1. So the worst case is big O(n), where n is the length of s. This is just math, comparison, return. So at worst here, because this is sequential, it means big O(n) plus big O(n) is big O(n). So big O(n) is the time complexity of this solution, where n is the length of the sequence, the string s. That's about it. Thank you for watching.